And now, our first presentation from Analytics Operation Engineering Incorporated, Adeline Kuo.
Thank you, Dr. Butler. Good morning, everyone. My name is Adeline Kuo. I am here representing Analytics Operations Engineering. With me today are my colleagues, Anjali Cannon and Gerald Vandenberg. And together we will be presenting our work on a scheduling tool that assists the New York City Department of Education with generating student-centered course schedules. Our agenda for today's presentation is as follows. I'll begin by talking about the motivation behind this project, as well as provide some context for the complexities in our problem. I will then hand over the presentation to Anjali and Gerald, who will explain to you our solution approach, as well as some of the challenges that we faced. I will then wrap up the presentation by going over our solution implementation, as well as discussing our future work. The New York City Department of Education has been experimenting with education models that focus on personalized learning for students. As a result, the Innovation Zone schools, otherwise known as iZone schools, were born. These schools offer students many ability-based tracks in multiple subject areas, and throughout the year, they wish to reschedule students based on their level of mastery in various skills. In order to customize student learning experiences, the iZone schools would like to build a master schedule that both allows students to take all their required courses and also enable students to take as many of their preferred electives as possible without violating any course capacity. They also need to adhere to all their resource constraints, such as their teacher, course, and room availabilities. Existing scheduling software used by the New York City Department of Education does not actually generate master schedules, but rather assumes that a master schedule exists and assigns students accordingly. What we've discovered throughout this project is that scheduling in practice has challenges that are not normally faced in academic research. For instance, there's the human element. It's very difficult to measure the quality of a particular schedule. And second, we cannot relax constraints of our choosing. And the big challenge is that we were under very tight time constraints for developing a model and a solution. So why is this problem so difficult? Well, individualized instruction results in a large number of constraints about which courses cannot take place at the same time. So for example, if a student is required to take both algebra and biology, then both these courses need to be scheduled for different time slots. And oftentimes, students in a particular grade do not take the same set of courses. And so therefore, this results in a large number of what we call of conflict sets. We also have a number of unique constraints to satisfy. So teachers' courses and rooms are subject to availability constraints. We have teacher union laws and maximum loads that teachers can take on. And often teachers need common planning periods with other teachers in the same department. Courses and rooms are subject to capacity constraints, and different courses can meet a different number of times in a particular scheduling cycle. Some courses can meet in single period sessions, while others in double period sessions, or a hybrid of both. Some rooms are only used for particular courses, while other rooms may have a little bit more flexibility. There are courses that are co-taught courses as well as team-taught courses. And what I mean by that is a particular course can be taught by multiple teachers, either by sharing the load of the course. One teacher will teach half the sessions, the other teacher will teach the other half of the sessions, or there may be two or more teachers in a particular course teaching simultaneously. And there are two types of schedules that these iZone schools would like to achieve. There's a ribbon schedule where courses that meet every day will meet at the same time every day. And then there's the non-ribbon schedule, where courses do not necessarily meet at the same time every day. And a non-ribbon schedule is not necessarily derived from a ribbon schedule by simply rotating the periods, because we have these unique constraints that we need to satisfy. At a high level, this is what our scheduling tool does. The user would input a set of requirements and run the scheduling engine. And the user could run the scheduling engine as many times as possible until a desired schedule is found. He can then, once he has reviewed all the schedules, either make manual tweaks to the schedule within the user interface of the tool, or publish the tool and distribute to everyone. I will now hand over the presentation to Anjali.
Now that Adeline has given you some background on the problem, I'm going to talk a little bit about how we approached the problem and developed our solution. Automated timetabling is a classic problem in OR with over 50 years of research already. However, we found that the problem faced by the iZone schools could not be easily reduced to any of the scheduling problems already studied. Some of the common problems that have been studied are the course scheduling problem, in which courses must be scheduled such that no students have two simultaneous lectures, the school scheduling problem, in which courses must be scheduled such that no teacher has two simultaneous courses, and the student scheduling problem, in which students must be placed into an existing master schedule. However, the problem, as we explained it, actually contains the constraints of all three of these problems, as well as additional constraints unique to the iZone schools, as well as a few more challenges that will be discussed later in this talk. So I've listed here a few common approaches to these problems. However, it's important to remember that these are just sub-problems of what we're doing, and we could not easily fit any of these to the problem faced by the iZone schools. So there's direct heuristics, which are a simulation of how a human would approach a problem, reductions to graph coloring, network flow, other common problems, integer programming, and finally, more recently, evolutionary algorithms and machine learning algorithms. When we were choosing an approach to this particular problem, we wanted something that could be rapidly developed and modified, would have a reasonable runtime, and would be independent of any commercial software. So we considered integer programming. However, we did not feel that it met these criteria. First, it would be a very complex formulation that would not necessarily be as quickly developed as what we are going to present. And secondly, it would be very dependent on outside software, and this would be a problem if we were deploying it at many schools across New York City, particularly because of the cost. Instead, what we present to you today is based on a graph model. In this graph, there is one node for each meeting of each course, and one node for each period of the week. Then, edges represent the relationship cannot take place at the same time as. So for instance, there would be an edge between two courses that were taken by the same student because those courses cannot take place at the same time. There would also be an edge between two courses taught by the same teacher. And finally, there would be an edge between each course and the periods when it could not take place because of teacher or room availability. Once we have this graph model, the problem of finding a schedule that allows all students to take all of the required classes without violating any of the teacher and other resource constraints reduces to the problem of coloring this graph in K or fewer colors, where K is the number of periods in a week. Once we have this model, the job of our scheduling tool can be reframed as the following. We first take in our list of constraints and then use that to generate a graph representation. So for instance, here, there's an edge between geometry and biology because there's a student who's taking those two courses. Similarly, there's an edge between algebra and 1 because the algebra teacher is not free during period 1, and so on. Then we take this graph and attempt to find a coloring of K or fewer colors, K being the number of periods in a week. We do this by applying a series of common graph coloring heuristics, and we do a number of randomized trials with these heuristics. The one we use most is the sequential graph coloring algorithm, or the Welsh-Powell algorithm, which is highly dependent upon ordering. So we do many randomized trials with different orderings of the courses in order to try to find a coloring. Finally, once we achieve a coloring, we translate this back into a master schedule by matching the courses up with the periods that have the same color. And finally, the student schedules follow from this master schedule based on the student requirements. Gerald will now go into a little bit more detail about some of the challenges that this problem presented us.
So first of all, what you just saw is kind of the basic setup and constraints for our problem. We have a graph, we have a series of constraints, we translate that to a graph, we color the graph, and then we map that back to our master schedule. However, one of the things that makes this problem really interesting is that we choose the constraints, and therefore we choose the problem that we're going to be solving. And some problems are better than others, and we define better by a problem that allows us to find more feasible schedules. And so before we even get to the stages that Anjali just applied, we need to make choices about the constraints that we use. And the key decision here is which edges to draw, or going back one step, which conflicts we want to use. So as a very basic example, there may be a student who can take one of two science courses, but he has a known math course, in this case algebra. Then we can choose to create a conflict between algebra and biology, or algebra and chemistry. And those will have different implications on our solution. So from a process perspective, we start by fixing these requirement constraints, and I will go into how we do that. And this is a process that's randomized and different over time to explore different areas, regions of the state space. We then draw our graph representation. We map our constraints to our model. We attempt to color it. And then if we're successful, we move on. And otherwise, we fix a new set of constraints and attempt to color our new graph. So coloring a graph is the one perfect measure of a score of a potential set of constraints. However, this takes time. And we want to build this graph sequentially, and there is no set measure of the increase in coloring and complexity as we are adding edges. So what we do instead is we first seek to minimize the total number of edges. The more edges there are, the higher the necessary coloring and the higher the complexity. In addition, when we are making choices between two edges, we use the maximum vertex degree as a measure of the colorability of a graph. Why do we do this? It is well known that it is possible to color a graph with k colors, where k is the maximum vertex degree plus 1. This is a ceiling and a proxy, but it makes sense from a coloring perspective to try to spread out the edges among different nodes. So instead of having one node with 20 edges, we may have two with 10, and that will lead, likely in most cases, to a lower coloring. In this particular example, we have 3 students who are all in an algebra course, and they have a set of choices between science courses. And although we could implement all these edges, we choose to remove one edge to make our graph easier to color. An additional factor of complexity is that in some cases, our algorithm will not terminate with a coloring that satisfies the number of available periods. And then the question is, how do we proceed from there? How do we get the closest acceptable schedule possible? And what we do here is we look at the weights of certain edges and remove edges with very low weight. So an edge with high weight is one where a lot of students have this conflict, and we will be affecting many of them and moving a lot of them between different classes. An edge with low weight will affect fewer students. So in this case, Mitchell has a constraint between algebra and biology. That is the white edge that we see. And what we do in our final coloring is that we violate this constraint and color them the same, and he will have to be transferred to another class. However, this means that for Adeline, Anjali, and Gerald, the schedule will be maintained, whereas removing some of these other edges would affect more students. Once we have taken care of the required courses, we also want to schedule the electives for students. Now, students will input a ranked order of their preferred electives. And the goal is, of course, to give as many students their preferred electives as possible. However, there's a trade-off here. We can do that, but then there may be a large lack of equity between some students who get their top 5 and others who get none of their top 5. So we want to maintain some equity across students. So to balance those two goals, our approach is twofold. First, we schedule the most popular electives first. This way we can put as many of them there as possible and fit that into the schedule. Second, if a student is not able to take his preferred first elective, we move him up in the priority queue for his next elective. So due to capacity constraints, what we do is we do some pre-scheduling. We ensure that everyone can take a certain set of electives, and if they can't, we move them on to the next queue. Finally, there is the course capacity issue. As I mentioned earlier, we want to minimize the number of edges to make our graph have a lower minimum color. However, there are some cases where it may be feasible not to have an edge from a graph perspective, but that course capacities would not allow that. So going back to my example at the beginning where there's a choice between algebra and biology and chemistry, if we play that up at a large level for, say, an entire grade, and all students are in algebra, and all students have a choice between biology and chemistry, but there are 2 sections of the algebra course and just 1 for each of the other courses, then it may be the case that we can remove an edge from a scheduling perspective, but that we can't have 100 kids in one of our science courses, that we need some spread across the 2. So we need to keep capacity into account when we are generating these minimum conflict sets. And so this is an example with chemistry and physics where we cannot remove this edge because then we will be violating capacity constraints. So that has to be taken account even as you are developing your conflict set. Just to review, this is kind of the overall algorithm putting all these pieces together. So we start by constructing the graph. We fix the set of constraints, something that changes randomly over different iterations. We decide which problem we want to solve. We then try to solve this problem, and we try to color the graph. If we achieve a complete coloring, then we move on to scheduling electives and then assigning students to the schedule. If we go through a number of trials and do not achieve a complete coloring, but come close, we will finish coloring the remaining graph to minimize the student impact, and then move forward with this schedule and schedule their electives, and then assign students to this schedule. Okay, and Adeline will now come back and tell us how this is implemented at the iZone schools in New York City.
In the next 2 slides, I want to give you a glimpse into the user interface that we deployed to the iZone schools. Here we have the user interface and sample inputs that go into the tool, such as which teachers are teaching which courses and what are some of the student requirements. Here we have some of the sample outputs, and as Anjali mentioned earlier, and Gerald as well, due to the randomized nature of our algorithm, we can output a diverse set of schedules for the user. And this is helpful to school principals who sort of lack a clear objective and would like to see a variety of schedules and make a decision, a qualitative decision, based on a number of options. We have introduced our iSchedule tool to 3 schools, and below is a testimonial from the principal at Queens Collegiate, Jamie Dubé. Key point that she makes is that our tool is customized to her needs. So we take into account all the constraints that she faces in her particular scheduling situation. There are a couple improvements that we would like to make to the tool. On the algorithmic side, we would like to explore incorporating evolutionary or machine learning algorithms into the graph construction and graph coloring piece. We'd also like to provide better feedback to the users about some of the scheduling bottlenecks so that they can reprioritize their goals. And part of the motivation behind some of these improvements is that New York City would like to get more schools on board each school year. To sum up our presentation, we have shown that individualized instruction poses a novel and challenging scheduling problem. Our iSchedule tool presents one possible solution based on randomization, graph theory, and direct heuristics. We have shown that implementation at iZone schools is successful, and we would also like to explore other other types of algorithms to both improve the quality of our schedules and also the runtime of our algorithm.